We'll move on now. Next is Yongda Zhu, and his talk is titled "Chasing the Tail of Reionization Using Dark Gap Statistics in Lyman-alpha Forest."
Okay, can you see my slide?
Yes.
Okay, hello everyone. My name is Yongda Zhu. I'm a third-year PhD student at UC Riverside. I'm very honored to have this opportunity to introduce our new observations near the end of reionization using dark gap statistics. This work is done with Professor Judge Becker and the XQR-30 collaboration. So I will start with a brief introduction of our scientific case, our method, and finally the results and discussion. So the scatter in Lyman-alpha opacity measurements below redshift 6 and the observed long trough towards J0148 extending down to around redshift 5.5 have indicated that reionization may end later than previously believed by redshift 6. And more evidence for an ultralate reionization also comes from the significant evolution of metal absorbers from redshift 6 to 5. For example, this is the O1 absorber. And most importantly, as Chris just mentioned in his talk, the recent measurements on the mean-free path of ionizing photons also favors a late reionization. In addition, semi-analytic modeling of variety observations also prefer a late reionization. Therefore, we are interested in whether reionization continued much below redshift 6, and how this can be distinguished from different models based on the Lyman-alpha forest. So to answer this question, firstly, we want to find out whether there are neutral patches in the IGM below redshift 6, or are there any signatures of this neutral IGM? So we need to quantify the redshift evolution of the Lyman-alpha-opaque regions. One way to do this is identifying individual dark gaps in the Lyman-alpha forest, which might be caused by the neutral IGM patches. And dark gaps are pretty useful here because they can provide complementary information to the opacity measurement. The tau effective measurements are usually done over large windows, for example, 50 megaparsec over H. The size is shown in this orange box, while dark gaps can provide multi-scale information of the IGM. In this work, we define a dark gap to be continuous regions of a spectrum in which all pixels spin to 1 megaparsec over H have an observed normalized flux less than 5%. And our sample include 56 high-quality spectra of quasars at redshift from 5.5 to 6.5, including 23 new spectra from the XQR-30 program. The XQR-30 is a VLT Large Programme targeting 30 bright quasars at redshift higher than 5.6. And Valentina will give us a talk on XQR-30 program in section 3A tomorrow, so please look forward to it. And finally, by the way, as shown in the blue line, we use PCA to fit the intrinsic continuum of quasar, so which is less biased than the conventional parallel fitting. And this figure shows all dark gaps detected with length and their central redshift. The red dots are dark pixels containing metal absorbers, but in total, we detected 49 troughs longer than 30 megaparsec over H, and we display the most interesting ones on the right. So just to draw your attention, firstly, we detected two long dark gaps completely below redshift 5.5 and extending down to 5.3. Both sightlines are from the XQR-30 program. Then still below redshift 6, in addition to the famous J0148 sightline, we got another 2 long dark gaps. And here in the bottom, we also display one extremely long trough that has a length of 160 megaparsec. Please note that most small peaks inside each dark gaps are scarce subtraction residues, as are indicated by the flux error ray colored in red. And this figure shows an overview of our results. Blue shaded regions are the Lyman-alpha forest, and the black bars indicate dark gaps longer than 30 megaparsec over H. And this figure shows how Lyman-alpha-opaque regions evolve with redshift in an intuitive way. You can see the 2 long dark gaps below redshift 5.5, and as the redshift increases, there are more and longer troughs. But in order to quantify the evolution of dark gaps, we need to use statistics. The first one is the distribution of dark gap length, and we also introduce a new statistic, F30, which is defined as the fraction of quasar sightlines passing through dark gaps longer than 30 megaparsec over H as a function of redshift. So you can imagine a vertical line sweeping along this figure. Here we use 30 because we found that in later reionization models, dark gaps longer than 30 megaparsec over H are likely to contain neutral hydrogen. This figure shows the evolution of cumulative distribution of dark gap length over redshift 5 to 6. You can see a strong evolution below redshift 6. And then this figure shows our main result, the F30. We can see that at redshift 6, about 90% quasar sightlines are passing through long gaps, and this fraction becomes 60% at redshift 5.8, and still 15% at 5.6, and the last long dark gap, the long dark gaps persisting down to redshift 5.3. So a good reionization model need to be able to reproduce this result. So in this work, we compare 3 different models, including the baseline homogeneous UV background model and several later reionization models, and finally a fluctuating UV background model, wherein reionization ends by redshift 6, but containing large-scale fluctuating UV background. Here is the comparison between the models and our dark gap measurements. The black curve in each panel shows F30 from the observation, and color shaded regions represent 68 and 95% limits of model predictions. As just mentioned, F30 increases with redshift. The non-zero F30 caused by low redshift dark gaps may suggest that the signature of reionization continues all the way down to redshift around 5.3. Then let's look at the first panel. It compares F30 from the data to the prediction of the homogeneous UV background model. It's evident that fully ionized IGM with a homogeneous UV background is disfavored even down to redshift around 5.3. And then let's look at later reionization models, wherein reionization ends around redshift 5.2 or 5.3. They are all consistent with the observation, except for this one. Oh, sorry. It's in the green box. It's a gradual reionization model with a high midpoint. It's less favored by the observation, and this result is also consistent with the CMB measurements. The rest one color in purple is a fluctuating UV background model. The low UVB regions can also produce long dark gaps. So overall, obviously, both later reionization models and the fluctuating UV background model are consistent with the data, at least over the available redshift range of simulations. The further constraints on these models may come from simulations over a larger redshift range and or different types of observations. As for our next steps, we are working on distinguishing these models using dark gaps in the Lyman beta forest, which can be used to trace more opaque regions, and perhaps they include more information. Another robust constraint, of course, will come from the mean free path measurement between redshift 5 to 6, which will give us a better understanding of the IGM evolution near the end of reionization. That's it. Thanks for your attention, and any question?
Thank you, Yongda, for a very nice talk. We'll wait 20 seconds.
Thank you.
All right, so that's the first question. How significant is the line of sight effect in your statistical analysis, following through long filamentary structure versus cutting through the filamentary structure?
This is a great question. So in this work, because we use a large sample, so we assume this effect is not so significant, but we do generate the mock data set to match all of our observation line of sight. So as you can see in the simulation results, they are based on 10,000 realizations with 56 mock data set for each model. So yeah, this is how we handle this effect, but it should be interesting to see the environment of this line of sight in the future.
Okay, the next question is a two-part question. The first one is, any physical reason for choosing 30 megaparsecs as the threshold? And the second part is, the second part is, in comparison with simulation, did you consider the noise levels of the individual quasar spectra?
Thanks. This is a great question. So as you can see in this slide, I calculated the dark gap distribution with and without neutral islands inside. As you can see in the later reionization models, which including the residual neutral islands, you can see starting from like 25 or 30 megaparsec over H, the distribution is dominated with the dark gaps with neutral islands inside. So that's why we use the 30 megaparsec over H as a threshold. As for the second one, for each quasar line of sight, we generate a set of mock spectra, and we tried to match the pixel size and noise level.
Okay, I'll ask the next question. If the long troughs at redshift 5.3 were actually damp Lyman-alpha systems, how metal-free would they have to be to have avoided detection as metal line absorbers?
So well, well, this is a great question, and I haven't I haven't thought about how metal-free they should be, but at least in our work, we inspect all of the infrared spectra to search for potential metal absorbers, but we found that even with the strongest DLAs, they cannot create 30 megaparsec average dark gap by themselves. So I think even they contain metal absorbers, it still will not be a very huge problem for this project.